Hi, in this video, we want to take a look at map projections with ggplot. Okay, so if I'm going to be plotting a map, whether I like it or not, there will not be a perfect representation of the area that I'm talking about in my map. There will always be a difference. So take a moment and think about what is a map. Well, it's a two-dimensional representation of part of the Earth. Okay. Well, a two-dimensional representation, it's kind of like the coordinate plane. Sounds kind of mathy, right? Well, so when we look at maps, we want to understand like the connection between the Earth and what we're looking at in terms of like a more mathematical point of view. All right, well, no matter what we do, there will always be some distortion. The Earth is not flat. Even if I'm looking at a small region, it's not perfectly flat, but my representation of it is. So in some way, some shape, some form, there's going to be distortion. Okay, well, what we want to talk about here is different representations so that we can get the best representation for the problem that we're working on. Okay, so in general, there's going to be two aspects that we focus on when we talk about distortion: shape of like boundaries, shape of countries, shape of islands, and also area. All right, so shape and area are the two things that we really focus on when we talk about the distortion. Now, the examples that we're going to go through are modified from Hadley Wickham's book, ggplot 2, Elegant Graphics for Data Analysis. Here is his GitHub page. And if you read through this text, Hadley refers to himself and he refers to the book throughout the text I'm going to be scrolling through. That's not my words, that's his. When you see the word I, that's Hadley referring to himself. All right, well, when we talk about projections, there's two things that we really need to think about: the shape of the planet and the shape of our map. So if I have the shape of the planet, we initially think of it as a sphere, much like a globe. But that's not quite right. It's actually not quite right by quite a bit. So something we could do to make that a little bit better representation is that we could go with, instead of a sphere, we can go with the ellipsoid. Well, what's the ellipsoid? Think about taking like a ball and stretching it or compressing it in perpendicular three-dimensional directions. And so kind of like a smoother football shape is a good way to think of it. All right, that's a better mathematical model of the Earth, but that's still not good enough. So what we could do, we could say that each, like a local region of each part of the Earth that we're interested in, we take the surface of an ellipsoid that fits well to the region we're interested in. That improves our model quite a bit. So this approach, we can get a better representation of the planet with these little ellipsoids throughout. Now, as a data scientist, I really don't care about these aspects. If I am, working on an international level, working with satellites, GPS, stuff like that, I care about. Maybe I'm, if I'm talking about navigation for ships across the ocean, this is a big deal for me. But for us as data scientists, we don't really need to get too deep into the weeds. We just need to know that there's issues. All right, so once we understand like the shape of the planet and our mathematical model of the planet, then when I go to make my map, remember that I have a two-dimensional representation of a three-dimensional object. So there's going to be distortion no matter what. All right, so the Earth is neither flat nor is it a perfect sphere. It's actually quite a bit off from a sphere. And so, this is going to come up if I want to like start really scrutinizing my maps. Now, here are some questions about how we are representing the Earth with our mathematical model. How ellipsoidal is the Earth, as if I want to represent it with just one ellipsoid, or how ellipsoidal is the region I'm interested in if I'm going to just take like a surface representation. Where is the center of the planet? This is important for GPS. Where is the origin point for latitude and longitude? Where is the sea level? And how do the tectonic plates move? And all these things are relevant depending on the problem I'm working on. And the geodetic datum is our representation of the Earth mathematically. All right, so there's several different choices that we might consider. So if I'm interested in North America, it'd be very natural to go with the North American datum. I mean, that'd be a good choice. But if I'm interested in, let's say, Australia, that's not going to be such a good choice. Another one is if I want to look at things for the world as a whole, the world geodetic system will be better if I want to look at the entire planet. All right, so as much as possible, we want our datum to be focused on the area that we're interested in. All right, so if I am interested, let's say, in the northern portion of South America, the North American datum would not be a horrible choice, but it would be a little bit off, right? I want one that would be centered on the region I'm interested in. And in general, like the larger the region we're dealing with for mapping, the more of a distortion we're going to end up getting. So the Earth is approximately ellipsoidal, but we're going to be drawing our map on a two-dimensional plane. So no matter what happens, there's going to be some problems. All right, so how to think about this from a math point of view. Think about Taylor's theorem. All right, think about a function that has a Taylor series. So if I have a function that has a Taylor series, I can always approximate the function with a reference point and a degree 1 polynomial. Now, if my reference point is close enough to the point I'm interested in, it's a good approximation. The farther away, the farther the distance between my reference point and the point I'm interested in, potentially I could get worse results. And so really a good way to think about this is that we're doing something similar to a two-dimensional Taylor's polynomial. So yeah, it'll be degree 1 in two directions, x and y. All right, so when we talk about the properties of our maps, there's two major things that we want to preserve. We want them to be area preserving and possibly shape preserving. Unfortunately, we can't have both. We could kind of give up a little bit of area, give a little bit up a little bit of shape, or we could go all in on area, all in on shape. But either way, we have to give a trade-off whether we like it or not. All right, so we have something called a coordinate reference system. And this is a complete set of assumptions used to translate the latitude and longitude into our two-dimensional map. All right, so let's go ahead and let's look at some examples. So I'm going to go ahead and use the Oz Maps package in R to grab a map of Australia. And so this is from the Australian Bureau of Statistics. And I'm just going to grab the voting regions for Australia. All right, so if I grab, so the SF package gives me a function that enables me to easily grab the coordinate reference system for map data. And when I grab that, I can see that our coordinate system is 4283. We'll look at this again in a moment. We can see that geocentric datum of Australia, and it was established in 1994. Here are the ellipses. Here is the ellipsoid used to approximate the surface. We can see that we're referencing latitude and longitude off of Greenwich. And we can keep digging in on the information. And so here very nicely, it tells us what is the area that is this is intended for. And here is the box in terms of latitude and latitude of where we're mapping. All right, there's something that's called well-known text, is a character string that describes our coordinate reference system also. For us, usually as data scientists, we just grab what's available, we grab the best one for the problem we're working on, and we're done with it. All right, so here, something that we could do if I wanted to just grab the 4283, I can see that I'll get the same thing either way. So I can specify off of the map, or I can give a number for the reference system. Now, remember, when I'm doing mapping, my coordinate SF is how I'm going to execute a lot of my mapping. And I absolutely must use coordinate SF if I want to make sure that I have things to scale. Otherwise, R is going to try and fit the entire plotting region, which will further distort my map. All right, so let's go ahead and just go with the defaults. Slap this on there. And we see a nice, beautiful map of Australia. Now, this time, and I personally can't really see a difference, but this time what I'm going to do is I'm going to plot the same data set, use the same geome, but this time I'm going to specify my coordinate reference system. So I'm specifying I want the 4283 coordinate reference system, and boom, we've got it. All right, so now if I look at 4326, this is a common one for GPS. And so this coordinate system is based off of the center of Earth's mass. And so this is a very common one, very good one if I'm using larger regions, if I'm interested in the Earth as a whole. And so we can see it. Visually, it really doesn't make a difference a lot of times what we pick, as long as we make a reasonable choice. In a few moments, I'm going to show you ones where things went sideways. Now here, if I go with 3857, that is the Mercator projection. And this is used by Google Maps and OpenStreetMap. So it's good to know this as I work through, so if we start using the Google features in R or in any project really, it's good to know how are we getting our coordinate reference system going. And so once again, I get a map. Yeah. All right, now let's look at another one. This one, 7789, is the International Terrestrial Reference Frame, established in 2014. It's an Earth-fixed system that is independent of continental drift. Okay, so this one, let's see what happens. Look at that. Mathematically, all the information from the data set is there. It's just that I've got the data in the file, and that is a mathematical approximation of what's going on in Australia, and then which that itself is only an approximation, and then I'm mapping that over to a two-dimensional surface. And here we can see a more obvious distortion of the geographic region. Now here's another one. If I want to go 2882. So that, it's not how we normally look at things, but it's still informative. 2882 is focused on West Florida, and that's why this is so off. Looks so strange. Doesn't it look strange? Now, what if I want my coordinate reference system to be focused on the North Pole, Alaska, but I go through and I map Australia? Let's see what happens. Well, if I take the coordinate reference system 3,572, and I plot it, just like we've been doing with geom SF and coordinate SF, I can see that's pretty distorted, right? It's hard to interpret what's going on. Mathematically, it's still correct. Doesn't mean that I can interpret it as a human being, though. All right, now for the rest of these, I just started like typing in like random numbers and just to get different coordinate reference systems, just to see what they look like. I think it's interesting to see what the latitude and longitude lines are doing with these different coordinate reference systems. All right, so I'll go back up to this one. So that's a good stopping point. All right, well, that's all I've got for you. Take care and goodbye.